What are white holes? Could white holes actually exist? The mathematics of white holes is consistent with general relativity. But does that prove that they exist in the real world? All the talk revolves around black holes. Yet, what about white holes, their mirrored counterparts? Could they be real? If so, then where are they now? The considerably more common black holes must be studied in order to grasp the nature of white holes. In the case of black holes, gravity has won out over every other force in the universe, and the matter in the area has been crushed to an infinitesimally small point called a singularity. An event horizon defines the region around a singularity when gravity is so intense that not even light can escape, although it is not a physical limit. Black holes are formed in the same way that we know about. A black hole is formed when the center of a large star is crushed to the point where it no longer radiates light. Objects, whether made of matter or radiation, that stray too close to a black hole are devoured by its immense gravity and sucked in beneath the event horizon. Einstein's general theory of relativity helps us make sense of the development of black holes and their interactions with their surroundings. Understanding that general relativity is time-independent leads us to the idea of a white hole. The equations are time-symmetric, thus they can be solved in either the forward or backward direction of time. This means that rewinding a movie depicting the birth of a black hole would reveal an object emitting radiation and particles. It would eventually explode, releasing a huge star into the universe. Since we are dealing with a white hole, everything is okay from a theoretical perspective of general relativity. The only thing stranger than a black hole would be a white hole. Singularities would still exist at their cores, while event horizons would mark their perimeters. Even then, they would be enormous, gravity-pulling objects. However, anything falling into a white hole would be instantly ejected at a speed faster than the speed of light, making the white glow flash fiercely. Nothing outside a white hole has a chance of entering it, as entering requires traveling faster than the speed of light, which is impossible. But if the mathematics of general relativity permits white holes, then why don't we think they exist? The correct response is that there are other explanations for the cosmos besides general relativity. Our theories of electromagnetism and thermodynamics are just two examples of the many subfields of physics that shed light on the nature of the cosmos. Entropy is a notion in thermodynamics that, in a nutshell, quantifies how disorganized a system is. In accordance with the second rule of thermodynamics, the entropy in closed systems can only increase. That is to say, disarray tends to grow with time. Take the case of a piano being fed into a wood chipper as an illustration. A cloud of fine dust is released. The system has become more chaotic, which satisfies the second rule of thermodynamics. Throwing a bunch of miscellaneous parts into the same wood chipper won't result in a fully completed piano, though, because doing so would reduce disorder. Complex, highly structured systems, such as life, are possible on Earth, but they increase solar entropy. No matter how well you design your system, wood chippers will never produce pianos. No star has ever suddenly appeared from a cosmic explosion, thus it's not possible to just reverse the process of black hole production to create a white hole. While general relativity takes a neutral stance on whether or not white holes exist, thermodynamics strongly rejects the idea. A white hole can only arise if an unusual mechanism occurred in the early cosmos and encoded the possibility of white holes into the very fabric of space and time. Since the white hole would already exist from the beginning of time, the formation process wouldn't have to worry about lowering entropy. White holes would be rather unstable, unfortunately. They would still attract matter due to gravity, but nothing could approach them because of their enormous event horizons. Any object, including a single photon, a particle of light, would be destroyed the moment it got close to a white hole. The system's energy would surge if the particle reached the event horizon, but was unable to pass it. The particle would eventually have such immense energy that it would cause the white hole to collapse into a black hole, thereby destroying it.